Right, here we go, section 2.5, looking at our complex or imaginary numbers. So quick reminder on those guys. I know you saw this in Algebra 2, but where do we get the value for I? So I comes from the square root of -1, right? That's our value for I. So obviously we know there is no real value for the square root of -1. So the idea is, what can we do in order to continue doing a problem and continue working with the values under a non-real value scenario? So we use this value I for imaginary, which represents non-real values that we're working with, but it still allows us to work with it. And you'll see on this one here in a second how this can sort of come together. The one thing I would say is, keep in mind that if I represents the square root of -1, well, if I square both of those, right, that tells us that I squared is -1. Okay, and that's going to come into play as we do problems like this. So if I wanted to take these factors, we're going to do a couple things. We're going to write it back into standard form, which means I'm going to multiply them together. I also want to identify the zeros. So I can identify the zeros just based on the factors. Remember, if we set this equal to 0, if I set each factor equal to 0, what would be the 3 zeros? So obviously this one becomes +5. If I set that equal to 0 and subtract this over, I get -2i. And for this one, I would get +2i. So those would be the 3 zeros. But we're going to put it back into standard form by multiplying all this together. I would start with those two. You could pick any two, but obviously we want to multiply these guys together, because in doing that, I'm going to get this idea right here, and that's going to allow me to simplify things. So hold off on him for just a second. Let's do a little distributing here. Keep in mind, these are called a difference of two squares. There is a shortcut to this. I'm going to mention it here in just a second. I'll show you where it comes from though. So if I start my FOIL process, so x squared, if I keep going, I would get a -2i here. I would get a +2ix here. Sorry, this would have been -2ix. This would have been +2ix. Those middle terms cancel. So I'm just going to do the ones that are not going to cancel. And I'm going to get -4i squared, which looks like this. And so just in multiplying those two guys together, this is what we have left. You can always take that shortcut anytime you see conjugates, which are the same factor, but one is positive and one is negative. Right? That's always going to allow those middle terms to cancel. So you only really have to do the first terms and the last terms. To simplify this one step further, like we just talked about, we know this idea. So I can turn this I squared into -1. So we're going to see this as -4 times -1, which is going to give us x squared plus 4. Let me bring down that x minus 5. So you'll notice, guys, in doing that, I no longer have an I in my setup. And under these conditions, that will always happen. So as you take any of these factors and bring them together, you should no longer have an I in your problem. And so as you get back to standard form, that should always be the case. You should only have x's and constants. You'll never have an imaginary in the original polynomial. All right, one more round of distributing. Distribute here, we got x to the third. Right here I got plus 4x minus 5x squared minus 20. So as you go through your distributing, obviously there's no common terms to combine, so that's going to be our answer. Of course, these guys can be switched. So standard form usually goes in descending order by exponent. Always put the constant at the end. So that would be the best way to write that answer. So one more idea I want to show you at the bottom of the page. Based on what you see right here, whenever it comes to imaginaries, or radicals, because remember there's a huge connection between imaginary numbers and radicals. Whenever it comes to those type of zeros, for every positive there will also be the negative, right? And so that's kind of explained right here. So complex conjugate zeros, so basically says if you have a positive imaginary, you must also have a negative imaginary. And again, that works for radicals too. So if the square root of 2 is a 0, then the negative square root of 2 must also be a 0. So just to give a couple examples for your notes, so if positive 3i is a 0, the negative 3i must also be a 0. If 2 plus I is a 0, then its conjugate, 2 minus I, must also be a 0. Okay, and so again, the same thing would work for radicals. If the square root of 2 is a 0, then the negative square root of 2 must also be a 0. Okay, and so keep that in mind as we move forward here. Let me take you over to some of our other problems here. And let me just try to focus in a little better for you if I can. Okay, so what you're seeing right here is the same thing that we did at the beginning of this video, but this one's going to be a little lengthier. So instead of working it all out, because the process isn't really any different than what I've already done, I just want to give you something that would make things a little simpler with some of the bigger problems. So if you look right here, so they're saying that negative 2, positive 1, and 3 plus I are zeros of a certain polynomial. Well, as we just talked about, if 3 plus I is a 0, then 3 minus I must also be a 0. So they're not giving you this one. We just need to know that it's there, because if this is there, then its conjugate must also be there. Okay, and so that's implied. So we would automatically need to note that and bring it into our solving process. So what we're going to do is, if negative 2 is a solution, what factor created that negative 2? Well, as we've talked about in an earlier video, that if negative 2 is a 0, then the factor that it came from would have been x plus 2. This would have been x minus 1. What about something like this? So here's where it gets a little trickier to identify those. The way you can look at any factor, and this is what will help with these guys, is to simply say x minus whatever the 0 is. Right? So if I could see this as x minus negative 2, well then there's its factor that we already mentioned, x plus 2. If I see this as x minus 1, right, then there's the factor for him that we've already talked about. So if I said x minus 3 plus I, that would look like this. And if I said x minus 3 minus I, that would look like this. So you can always say x minus the 0, whatever it is, in order to identify your factors, right? So there's the layout that would look like this. They kind of went from here to here without really showing you how that was done. So all we're doing on this problem, just like what we did in the start of this video, is distributing, right? So we're going to do a whole lot of distribution, or FOIL, as you guys know it. So they multiplied those two guys together in order to get this expression. They distributed all of this together in order to get this expression, but they didn't really show you the math that went into this. So that's what I did over here on the side that I wanted you to see. I'm going to show you a little bit of a shortcut, kind of. At least it's the quickest way to go. So what I would have done first is I would distribute that negative. So I'm going to see this as x minus 3 minus I. So that's what I wrote right here. I'm going to see this one as x minus 3 plus I. That's what I wrote right here. The way that I simplified this goes back to what I showed you at the beginning of this video. When you have conjugates, and I'll just write it out really quick. Remember, conjugates mean you have the same factor, but one's positive and one's negative. Right? When you have conjugates, the idea was the middle terms will always cancel. So I really only have to do the first ones, a squared, and the last ones, negative b squared. Right, that will always happen when you're multiplying conjugates, because the middle terms would cancel. Right, if you looked right here, this would be negative ab, this would be positive ab, those guys would cancel. So this is all that needs to be done. So the whole purpose of doing this is to set up this scenario, right? So after I wrote these out, I'm identifying this as a group, so x minus 3, and I'm bringing down my minus I. I'm identifying this as a group, x minus 3, bringing down this, my plus I, right? So when I write it this way, now it fits this model, and I have something minus I, and I have something plus I, so that makes these conjugates of each other. So all I really have to do is my first terms, x minus 3 times x minus 3, and my last terms, negative I times positive I, right? So I'm doing this, right? My first terms minus the last terms. And that sets up this scenario right here. And so now when I FOIL this, right, which just becomes x squared minus 6x plus 9 minus negative 1, right? In other words, plus 1 because of the double negative. And that's where they got this expression right here. So there was a lot of side work that went into getting this that they didn't show you, so I wanted you to see that process. I know this is something you guys did in Honors Algebra 2, but definitely a good reminder because this usually is done first semester and a lot of people will forget this whole idea. So anyway, you would have another round of some really lengthy distribution going on here in order to come up with the final expression. But I know you guys can do all that distribution, so I just wanted to remind you of the process on doing that. Okay, let's jump down to this one. So when we get these really big polynomials that look like this, how do we break those down? How do we factor those? Or even if I were to say, what are the zeros? Like find all the zeros, like we've been doing this chapter. How do we do that for something that involves imaginary values? So as we look at this, so this is, sorry if it's a little unclear, I'm trying to make it as clear as I can for you. I'm looking at x to the 5th minus 3x to the 3rd plus 6x squared minus 28x plus 24. That's what's been graphed over here. So as I look at this, how do we start breaking this down? Well, as we know from earlier videos, if this is x to the 5th, I know that there are 5 zeros involved, right? There are 5 zeros. However, if you graph it, I can tell by the graph that there are only 1, 2, 3 real zeros. So if there's only 3 real zeros, but according to this there's supposed to be 5 zeros, what does that tell you? It tells you that the other 2 must be non-real or imaginary zeros, right? So I know that there are, according to the graph, 3 real and 2 non-real based on that. We did see in an earlier video how some zeros can get repeated. So you might say, well, maybe there's only 3 zeros, but maybe it's because 2 of them got repeated, right? Maybe there's 5 real zeros, but there was some repetition in there or multiplicity. So maybe they're all real, right? But however, if we look at the graph, we talked about a rule earlier on this chapter where if it is crossing over the axis, right, it's not bouncing off of it, it is crossing through it. That means there's only 1 zero represented here. If it was a multiplicity, meaning I was getting a repeating value, then I would see the graph bounce. So it would go like this. It would hit this and it would bounce and come back down. And that's where we see the repeating values. So if it's crossing through, that means there's only 1 value here. So I know based on that, I'm only looking at 3 real zeros. The other 2 must be non-real. So anyway, we're using 2 tools here to break this down. One is going to be with our graph, because the graph really helps us. We're going to use graphing calculator. Really helps us to identify some of our zeros, and then we're going to use those to find the rest with synthetic division. So that's going to be our other tool. We've already done this chapter, so this one I'm just sort of talking through, but we are going to do one together here from start to finish so you can see the process. So they graphed it. They said, okay, I got -3, +1, +2. Those are my 3 real zeros. We're going to use those with synthetic division to come up with the remaining values. So if I took any of those 3 zeros and started breaking this down with synthetic division, we could get it all the way down to here. This is what would be left, right? As I set this guy, there's two ways you could look at this. I'm going to show you both real quick. So if x squared plus 4 is a factor, we can break this down. I'm going to show you where these guys come from. So if I said x squared plus 4 is a 0 of this graph, well, as you subtract over the 4, and I get this, and I square root. So as we've seen before, I can't do the square root of -4. That's where the I comes into place. So we would simply say that x represents plus or minus. We know the square root of 4 is 2. Because it was a negative, we have to throw in the I to show that it was a non-real value. And that's where these two factors come in. So we have x plus 2i and x minus 2i as the remaining two zeros. And so now we can line them all up as factors and say here are the factors. Of course, the next step is going to be find all the zeros, right? So instead of just seeing the factors, if I set each one of those equal to 0, we can then list the zeros, which would be -3, +1, +2, -2i, +2i, right? Those would be the 5 zeros of the graph. So if they just say factor, this is how we would write it. If they say find the zeros, then we would actually list them out. So we're going to do that on this one. So here's what the full process from start to finish is going to look like. We're going to start by graphing it. So if you got access to your graphing calculator or Desmos, we're going to go ahead and take a look at the graph to help us get started. So this is, I'm going to write this one out so you can see it better. All right, so that's what we're looking at here. So there's a little more clear view of it. So I'll go ahead and take a second to graph this. So as we type all that guy in, it looks like this. I don't know if my basic Windows settings are going to work yet or not. We'll take a look at that in a second. I'm going to go ahead and hit graph. And remember, on these graphs, the maximums and minimums don't really matter. What we're looking for are the x-intercepts. So if it goes off my screen up here, I don't really care about that. What we care about are the x-intercepts. Okay, and so, however, based on this, looks like +1 and +3 are going to be some zeros for us. However, based on this, there should be 4 zeros. So it looks like from the graph that I am looking at 2 real zeros and 2 non-real zeros. So let's start with the ones that we already know. So from the graph, looks like +1, +3. So we're going to do some synthetic division here. Not only to verify that this really is a 0, but we're also needing to start breaking this down so that we can find the remaining 2 zeros. So this is really helpful for 2 reasons here. So let me pull over the coefficients. I got 1, -8, 32, -64, and 39. Make sure that we're not missing any values that I would have to fill in with a 0. So this goes 4, 3, 2, 1, constant. So we're good. Everything is covered. Don't need any placeholders. So bring down. You guys are experts on this by now. Multiply and add, multiply and add. All right, and sure enough, we did hit our 0, so we know this is the correct solution. That's an intercept. So let's take a look at what we got left. We're going to use the other value. So from here, if you can factor it from here, awesome. You should definitely factor it. If not, that's where synthetic division comes into play. So I'm going to use the other 0 that we saw on the graph to break it down one more time, because I can't factor it from here. Usually if there's 4 terms, we factor with grouping, but I can even see based on these numbers that grouping would not work. So I'm going to need to break this down one more time. So again, let me go through this process real quick for you so we can see what we got left. And just like we expected, I'm left with these two guys right here. So are these three values right here? We know it's a 0, went in evenly just like we thought. So we know that x minus 3 is a factor, or you could say positive 3 is a 0. Same thing. So as far as factors right now, we already know that I have x minus 1 and x minus 3 as factors. What about this? So how do we break down something like, if I put the x's back in, remember this means x squared minus 4x plus 13. All right, that's what we have left. I still got to break that down. So technically, I could write this as a factor, x minus 1 as a factor, x minus 3 as a factor. However, as I look at this, they still want us to break this down even though they're imaginary values and imaginary factors. If you look at the one that we just did right here, in the past, as we looked at this value right here, we would have said this is not factorable. This does not fit any of our factoring models, right? It's not a difference of two squares because it's a plus and not a minus. However, they still want us to figure out what are the values, and then we can simply say x minus this one and x minus this one, right, to write them as factors. So here's what that would look like. Because it's not factorable, how do we solve something like this? And that's where the quadratic formula comes into play. So I'm going to do negative b plus or minus square root b squared minus 4 times a times c all over 2a. So as we start doing a little cleanup on this, I'm going to have 16 minus, let's see, what would that be, 52? So 16 minus 52, which is negative 36. And we knew that would happen. We knew there'd be a negative under here because it's imaginary numbers. If I would have come up with a positive, I would have wondered what was going on here. That wouldn't have made sense. Okay, so we're going to simplify our radical. We know the square root of 36 is 6. Because it's negative, we have to say 6i. So 4 plus or minus 6i all over 2. Always simplify if possible. And remember, this is only possible if this number goes into both. So never, never, never do one of these without doing both of them. Right? Not the way we're supposed to simplify here. So because it goes into both, I know it goes into 4 twice. I know it goes into 6 3 times. All right, so those are my remaining zeros. So if the problem just said find the zeros, which this one does, but this one asks for two things. So it says find all the zeros. So I could now list my zeros like this. So if it said find the zeros, there you go. Those are my 4 zeros. Remember, we expected there to be 4 of them. So those are my 4 zeros right there. When it says write its linear factorization, we could also write these out as factors by always saying x minus whatever the 0 is. So I'm going to say x minus 3, x minus my 1, x minus 2 plus 3i, so it looks like this. And I'm going to run out of room right there, so I'm going to write it here, x minus 2 minus 3i. But that's it. That's the process. So if they ask for factors, it would look like this. Zeros, it would look like this. Okay, here's the last thing I'm going to show you. Again, I'm going to sort of talk you through their example. We're going to do 2 on our own, and we will call it a day. So here we go with x to the 5th minus x to the 4th minus 2x to the 3rd plus 2x minus 3x plus 3. So that's our polynomial that we're going to break down. They want it as a product of linear and irreducible quadratic factors with real coefficients. So here we go. So as we look at all that, what that means is they want you to break it down in the simplest terms possible while maintaining real coefficients. So in other words, based on this wording, they want me to factor it and break it down as far as I can. So if I want irreducible quadratic factors, that means if I have any quadratics, they want me to break them down unless it creates non-real coefficients. So if I get non-real values, they want me to stop. But if it's real values, they want me to keep going. So here's what that looks like. So if you're to go through that whole process that we just talked about within our last problem, again, I have 5 zeros. So I should have 5 factors unless, and like in this problem suggests, they don't want me to have any non-real numbers. So if they don't want me to have non-real numbers, I may not have all 5 factors showing like I did in the last problem. So as I look at this, I can see that there are 3 real values. My graph does not bounce off of any of those, so nothing is being repeated. I should have 5 separate zeros, right, based on this. And as I see in the graph, 3 of them are real, which means the other 2 are non-real. So if we started breaking things down like we've talked about before, if you were to graph this, this one was a little tricky. Based on what you see here, this is what they really did. It looks like this is a 2, but it's not. Based on the scale that they used, they were actually counting by halves. So 0.5, 1, 1.5, 2.5. So I was trying to show you that up here. They weren't using a 1-by-1 scale. They changed their scale. So if you graphed it, count by ones so it doesn't look confusing for you. Your graph would look a little different than theirs. As you can see, this is not the same scale that this is, right? You can see there's a difference there. So if you graphed it, your graph would look a little more obvious to you maybe. But anyway, all that is to say, this is +1. I really can't tell what those are, so I can't use those in synthetic division. So the only one we'd be able to use is this. So +1 would go in the box. I would break down the rest of this to see what's left. So if I put +1 in the box, here is what would be left. And so here we go from here. So now we're into kind of the quadratic stage because there's only 3 terms. So we would say what numbers multiply to be -3, that add to be -2, and these become the remaining factors. So here's all of our factors. So here's where this wording comes into play, and this is what I wanted to show you. They want me to break this down in the quadratic stage as long as it's not creating non-real values, right? And so as we look at these both are going to fall under the idea of our difference of 2 squares that we've already talked about. So if I have this, our difference of squares says we take the square root of each term, we make one of them a plus, and the other a minus. Right? That's the whole difference of squares conjugate idea. Okay, so if I take the square root of my first term, it becomes my a value. Square root of this term becomes my b value. We make one of them a plus, the other a minus. Right? That's the whole difference of squares factoring process. So if I look at this one, that's what we're going to do here. So I'm taking the square root of this, which is my a value, so x and x. The square root of this, which is not a perfect square, so we simply leave it as rad3. Right? We make one of them a plus, the other a minus. So that so far everything can be broken down because these are still real numbers. It's not rational, it's irrational, but it's still real, right? It's still visible on the graph. X minus rad3 and x plus rad3 are these two guys that you can see on the graph. So they are real, even though they're irrational, they're still real. So, however, this one, right, if we were to try to break this one down, this is not a difference of 2 squares, this is a sum of 2 squares. And as we've already seen in this video, if I were to try to solve that, it's not really solvable. So we would say this, if I square root them, we get imaginary numbers. So based on that, he cannot be factored and still be real, right? So if they want only real coefficients, then this one would need to stop here. I can't keep going like I did in the last problem, just based on the wording of these directions, right? If they didn't say this, we could have broken this down like we did in the last problem, and I could have said my remaining two factors are x plus I and x minus I, but just based on these directions, so this is why you got to always read directions really carefully and stop where they want you to stop. So let me go through these last couple. If you need a little extra practice, then keep going with me. These are the last two things we're going to look at. And I can already tell I'm going to not have enough room here, so let me bring in another piece of paper and we'll go through this real quick. One thing I did mention is take a look, because some things are, I wrote it right here, some things can factor without synthetic division or a calculator. As I look at this one, let me remind you of factoring by grouping. When I see four terms, what I look for is, can I factor these by grouping? So if I have 2x to the third plus x squared minus 14x minus 7, what I look at is, if I were to group the first two and the last two, I look at these groups, and I already know this is going to work because I can see by the numbers, but I wanted to remind you of how you factor by grouping. As I look at my first group, I'm going to take out the greatest common factor, which is x squared. That leaves me with 2x plus 1. And as I look at these, I can factor out negative 7. And that would also leave me with 2x plus 1. So here's when I know grouping worked, is when they're left with a common factor, like these ones are. So I'm actually going to factor out this as a common factor. So here's my first group. I'm going to pull out 2x plus 1. So I'm pulling that out of each group. So that's my first group, that's my second group, and I am factoring out 2x plus 1 as a common factor. What would that leave you with? It would leave you with x squared minus 7. And so I was able to break this thing down and factor it without the calculator, without synthetic division, long division, all those other tools. So if you recognize that something is factorable, go for it. You could still do the other tools, but I think this can get you there quicker if we do this right. So based on the directions that we saw up above, this is saying the same thing, irreducible quadratics. So I can do that. So he's done. He's linear. X to the first is linear, so he's done. This one is a difference of two squares. Because it's a difference, I know that this is not imaginary. It is irrational, but not imaginary. So this one I could now write as x plus root 7 and x minus root 7. And those would be my linear factors. So they're all x to the first. I did not need any imaginary numbers. So if you were to graph this, you see it's x to the third. You would see 3 x-intercepts on this graph, implying that all 3 of your zeros are real zeros. So let me take you over to one last problem. And I'm going to write it since it's a little unclear. So here we go. If I were to try to factor this one by grouping, I already know by the numbers it's not going to work out. I'm not going to be left with a common factor. So I'm going to have to go through graphing and synthetic division to make this work. So I'm going to throw that into the graph real quick. So let's go ahead and graph it. So let's see what we get here. So based on this, and it's always possible that my window's not big enough, so I could extend out my x maximum, and I could extend out my x minimum. However, I'm pretty confident that this is the only real zero in the problem. So as I look at this, based on that, I'm going to zoom in on that because I want you to see something. Enter. So this one's a little tricky because I know this is a real 0, but it is not landing on an obvious point. It looks to me like -1/2. So we're going to have to go with that, because if I need to try to break this thing down, I know based on the graph that I see and this number that I'm only going to get one real 0 and two non-real zeros out of this. So it looks like this is -1/2. So in order for me to do synthetic division, let's go with that and see if I'm correct. If I get a 0 at the end, I know it's correct. So we're going to give this a shot here. So 2, -11, 20, and 13. As I look at these numbers again, just make sure they didn't skip any terms, that you don't have to fill in any 0 placeholders on this. That's important. This does go 3, 2, 1 constant, so I'm good. Let's go through our process and see if this works here. So multiply and add. And it does. We found our 0, so I know this is a winner, so that is -1/2 right there. If it was not an integer, or I'm sorry, if it was not a rational number, then you wouldn't be able to go through this process. So what I see on this graph, and that's how kind of why I knew it sort of needed to be -1/2, is because it had to be a rational, or yeah, sorry, it had to be a rational number in order for me to be able to do any of this. So I know we could use that to move forward. Here's what's left. I now have 2x squared minus 12x plus 26. They want me to break this down and factor it as far as it can go to find my remaining zeros. As far as factoring goes, I definitely want to pull out the 2. Makes life way easier for factoring if you can do something like that. Something that you guys ran into in Algebra 2 last year is, when do I keep this and when do I get rid of it? And here's the answer. If you are only writing factors, keep it. If you are finding the zeros, you can get rid of it. Because if I am finding the zeros, anything that does not contain an x is not a factor that would produce a 0. Right? Only my x's produce zeros. So if I'm just listing out the zeros, I can get rid of him at this point. But if they want me to write out all the factors, then I should keep it involved. So again, this is not factorable. No products of 13 would add to be -6. So I do need quadratic formula. So -b plus or minus. So b squared minus 4 times a times c all over 2a. So simplify my radical. I am expecting a negative because there was only one x-intercept. And we already found what he was. So the other 2 must be non-real. So if I did 36 minus 52, I get -16. There's my negative. So 6 plus or minus 4i over 2. So it looks like this. And I'll show you why I'm going this far on this problem here in just a second. Divide everything by 2. I get 3 plus or minus 2i. Okay, so I have 1 real, 2 imaginary zeros. If the problem just says write all the zeros, I would list all 3 of those. If the problem says find the real zeros, I would only list him. Based on the directions we're looking at right now, this is a product of linear and irreducible quadratic factors with real coefficients. So here's what all that fun stuff means. As far as the factors go, I know that this is x plus 1/2. and I'm going to show you how you can rewrite that in a second here. So I could write it as x plus 1/2. So here was the other factor, right? I have him. I could take out the 2 and write it this way, and that's fine too. So if they want me to, if they just said write all of the factors like we did earlier in the video, I would then need to write x minus 3 plus 2i and x minus 3 minus 2i if they want me to write all the factors. Based on these directions, they don't want imaginary values. So if I look at this, then I would have to go back to this stage and say, okay, they don't want me to write imaginaries, so I'm going to stop right here. Sorry, I would factor out the 2 and stop right here. X squared minus 6x plus 13. So I would stop right here just based on the directions that I'm reading. So super, super important that you read the directions on how they want you to write those answers. One last little side note, you can alter this one and not leave the fraction if you don't want to, simply by taking the bottom number and putting it in front of x. It would become 2x plus 1, and so it can be written this way as well. So I've tried to cover all the possible scenarios that you can run into, as well as the possible directions that you can run into. So read careful so you know what they're asking for and how to write your answer. But that's it for this one.